Hello, in the last video I have shown you how to determine whether a ball will roll or will slip down the inclined plane. Today I would like to do the exact same thing, but starting from a different point. In the last video we have assumed that the ball is rolling and checked for what set of angles of inclination and frictional coefficient that is true. In this video I will assume that the ball is slipping and check for what set of frictional coefficients and angle of inclination that is actually true. So let's start. We have our inclined plane, we have a ball that's rolling down, and we know the ball's moment of inertia calculated by the axis passing through the center of the ball. So let's write again the mathematical definition of slipping, which is that that velocity v is greater than the angular velocity omega times the radius. And again, we will take derivatives with respect to time on both sides. So we get that A is greater than epsilon r. And now let's discuss forces, some forces acting on the ball. We have a component of weight that's pushing downwards. I will call it Fd. And we have a frictional force. In the case of slipping, it's a force of kinetic friction, Fk. Okay, so now if we have the force of kinetic friction, we know the exact value of that force, and it is equal to mg mu cosine of theta. And we also know the value of the force that's pushing downwards, that's perpendicular to the plane, and it is that Fd is equal to mg sine of theta. And we now shall write what follows from the Newton's laws. We have that ma is equal to mg sine of theta minus mu cosine of theta. Okay. And we have also that I epsilon is equal to the force of kinetic friction. The ball now is pivoting by its center. So the force of kinetic friction is g mu cosine of theta. Okay, and now it's just time to solve it. Here we can notice that masses will cancel, and I will substitute A into this equation, and from the last equation I will substitute the epsilon here. So what this equation implies is that epsilon is equal to mg mu cosine of theta divided by I. Okay, so let's write. Now I will write this. So we have that g sine of theta minus mu cosine of theta is greater than mg mu cosine. Oh, sorry. Here should be, of course, r. Here, r and r, because, yeah, r's. Okay, we have mg mu cosine of theta times r squared, one r from here and one r from here, divided by 2/5 m r squared, r's cancel, r squares cancels, and masses cancel. And now I will add the mu cosine of theta, so we are left with g sine of theta is greater than 7/2 g mu cosine of theta. G's cancel, I will divide by the cosine, so we get that tangent of theta is greater than 7/2 mu. And what follows from it is that theta is greater than arc tangent of 7/2 mu. So again, in this case, we have slipping, and for thetas smaller or equal to 7/2 mu, we have rolling. I think actually we need to write it that way, because if theta is equal to 0, we actually don't have the inclined plane. maybe it's not 100 correct in the form when you're considering logical mathematical statements, but I think you get what I mean.